Today's topic is transient stability study, and not only transient stability study, how to find out the critical clearing time for this generator. Critical clearing time, we will work out on this. Let's play with that critical clearing time or CCT values, and what are the parameters that impacts on the critical clearing time. What are the parameters or what are the factors that can influence this critical clearing time? So all these details, all these things we will discuss in detail. Maybe this video will be lengthy, but it will be helpful definitely. So let's start this topic. So already, just to minimize the time, we have this, we can see this model here. What I have done, I have modeled one generator of 300 megawatt generator, transformer 350 MVA rating transformer, generation voltage is 18 kV, and this is generator step up transformer. It is stepping up the voltage to 400 kV, and there are two transmission lines, means this is parallel transmission network is there, and this is another 400 kV bus, and also one grid is connected here. One grid is connected, and this is the grid details. 40 kiloamps, 40 kiloampere is the short circuit current, and X by R value is 20. So this is the model what I have already drawn, just to save our time, because today's focus will be on the transient stability study and how to find out the critical clearing time, just to maintain the grid stability or to protect this generator, and also what are the factors that can have the impact on this critical clearing time. So let's quickly move to this transient stability study here. Okay, now what we need to do before performing the transient stability study, what we need to do, we need to create event here, events. So what is the event? Let's say we are going to create a fault here in one of the transmission line network. Let's say in this transmission line network. Before that, let's give the line number also. So this is line number 16, this is 17. Okay, now go to event, add event. Let's say fault. We are creating a fault. We are creating a fault at 1 second. We are creating a fault at 1 second. Where we are creating the fault? We are creating a fault here in this line, transmission line. So this is line 16, in this line 16, and we are creating a fault, and at what length, at what location? Let's say this is 50% of this line length. That means this line length is 100 kilometer. This line length is 100 kilometer, and we are creating a fault here at 15% of length. That means at 50 kilometer length. From this generator side, this 50 kilometer length, we are creating the fault. Okay, just let's so this line length also, line length here, yeah. So 100 kilometer length, and we are creating the fault. So we have created this event, and let's say total simulation time is 10 seconds. Let it be there, and before performing that, we need to plot this. Let's say synchronous generator. So for this generator, gen 6 id, gen 6, let's plot here. and also the buses, this bus number 76 and bus number 77, 76 and 77. Okay, now the system is ready to perform the transient stability study. Let's run this. Yeah, and how to read, let's plot here. Let's plot here Gen 6 and okay, no need, only maybe this power angle, relative power angle, we can plot this. That's fine. So as you can see, from 0 second up to 1 second, there is no fault. There is no fault. But after 1 second, fault is created. Fault is created. So that's why it is going off. And this is the maximum value. This is the maximum value of this angle 178.5 degree. 178.5 degree. And again it is going down, again off and down, and this in this way. And after certain time, generator will be tripped, just to save the generator, because now here you can see this is 0, this is 0 degree, that means generator already tripped here. If the fault why it is now 0, why generator is tripped, means we have not given any trip command, we have not cleared any fault, we have not given any command to the circuit breaker to clear the fault. So that's why it has gone up to this 178.5 degree, which is not acceptable, and which is detrimental, and it can damage to the generator as well as the question mark. There is a big question mark in that grid stability. So just to save the generator and also to maintain the grid stability, we need to clear the fault here. At what time? At what time? So that is called the critical clearing time. So at maximum what time we can clear the fault so that the generator will be saved, generator, there will be no generator damage. Before damaging the generator, we can clear the fault, and also it can return back to its synchronous speed, and also to maintain the grid stability. So now what we'll do, next step will be, we'll clear the fault, we'll open the circuit breaker to clear the fault, and we'll see the case study how the system will behave. Okay, so go to this event here, and fault is created at 1 second. Now we need to clear the fault, we need to clear the fault, we need to clear the fault. So this circuit breaker, which circuit breaker, say this is CB15. CB15 will open this circuit breaker CB15, and since this is parallel transmission line is there, so we need to clear the fault from the both side, from the both end of this transmission line. That means CB15 should be tripped, and also CB17. CB15 and CB17, both the circuit breakers should be opened. Otherwise any one of the breaker can feed the fault, because this fault is created at the 50% of this line length, transmission line length, that means at 50 kilometer. So we need to open this circuit breaker 15 and circuit breaker 17. So CB15 and CB17. So circuit breaker 15, we're going to open this, and also another circuit breaker CB16, sorry, CB17, open. So okay, this will be opened, but we need to add event here. Sorry, we made a mistake. This is the fault creation means we have created the fault at this line at 50 kilometer 50% of the line length. We need to create another, we need to add another event which is the fault clear. Let's say fault clear at what time? At 1 second the fault is created. Let's say at 1.6 second. That means after the fault is created, after the fault is created means after 600 millisecond of the fault creation, we are going to open this circuit breaker. We are going to open this circuit breaker 15 and circuit breaker 17. CCT. Yeah. Now let's run this. Go to the plot, relative power angle. Yeah. So now what we can see, this angle is same 178.5 degree. So there is no change. That means the critical clearing time we need to change. Let's say this is 1.4, means after 400 millisecond we are going to open this circuit breaker 15 and 17. Yeah, now we can see the difference. Previously the fault was being cleared after 600 millisecond, but that was not recommended. And now you can see the fault is created here at 1 second. After that it is going off. So at maximum angle is 155 degree. Previously it was 178.5 degree. So now it is 155.3 degree and going down, off, down, and finally it will be normal. It will come to the normal range. But the question is it acceptable? Is it acceptable, this 155 degree, this 155.3 degree, is it acceptable? The answer may be no, because as you know, this pole slipping or out of step relay 78, that pole slipping or out of step relay 78 will give the trip command, to the generator, because that setting is recommended setting is, the default setting is 150 degree, and sometimes we set that relay to 140 degree, or maybe at a safer side 130 degree. So we need to clear the fault well before this 155 degree. That means the fault clearing time should be shortened. That fault clearing time should be expedited. That means if we change this fault clearing time, instead of 400 millisecond, let's say we are going to clear the fault within 300 millisecond, then what will happen? Yeah. So now the angle is reduced. Now it is 115.5 degree. Now it is 115.5 degree is the maximum. So this is well below the set point. If we set that angle, protection angle, in that relay 78 out of step relay, if that angle is set at 130 degree or 140 degree, so well before that it will clear the fault. That means it will not go out of step. The generator will not go out of step. That means the generator will not get tripped, and after some time the generator will be normal. But we can increase this fault clearing time also, because we have a buffer here, we have a margin. So if we set that relay 78 relay setting at this angle as 140 degree or 130 degree. So in that case we can increase the fault clearing time here. There will be no issue. Let's say 1.3 means 350 millisecond. If it is 350 millisecond, so this is the critical clearing time, whether 300 millisecond or 350 millisecond. How fast the fault will be cleared so that the system will not lose the synchronism, means the grid network will be stable, will remain stable, and also the generator will not get tripped or will not get damaged. So that is the purpose of this fault clearing time, and we need to find out. So this is now 131.4 degree. You can see this is, so if you set that relay at 130 degree, then it is also not acceptable, and if you set that relay at 140 degree, then this is acceptable. This fault clearing time of 350 millisecond, that is acceptable, right? This 130, this 350 millisecond is acceptable, right? So now what are the factors that can impact on this system stability or this this generator stability? So what are the factors? I will discuss some of the factors. So what are those factors? So factor number one is the fault location. Fault location. Suppose this is 100-kilometer transmission line, and we are we are creating the fault here. We are creating the fault here at 50 percentage of line length. So if we change this, let's say 20%, let's say 20% of the line length, that means at 20 kilometer from this side, at 20 kilometer the fault is created, and I am not changing anything. I am not changing this fault clearing time as 350 millisecond, and any other parameters I am not changing. Only what I have done, I have changed the fault location. Instead of 50 kilometer, now the fault is happening at 20 kilometer of line length. Now let's see what will happen. So previously it was 131 degree. So now you can see this is 177. Now it is 174. So which is not acceptable. That means there is a problem. That means there is a problem. So conclusion is, it depends on the critical clearing time. It depends on the location of fault. It depends on the location of fault, right? Now let's say the fault is at maybe 75% of the transmission line. That means at 75 kilometer, at 75 kilometer. Yeah, so this angle is 127.2 degree. So that means this much of fault clearing time is sufficient to clear the fault and to maintain the system grid stability, right? Because the fault is created at 75 kilometer away. So it depends on the fault location. So this is factor number one. Factor number two, grid parameters. Grid parameters. Let's say, let's change this. Let's go back to the 50 percentage. 50 percentage means at 50 kilometer transmission line, the fault location is at 50 kilometer, and the grid parameter, this is 40 kiloampere. 20 x by RDC is 20, right? Let's say this is a weak system. This is a weak system, or maybe 20 kiloampere. Sorry, this is 20 kiloampere. 20 kiloampere. This is a weak system, and now let's run this. So as you can see, this is crossing 150.3 degree. That means this is also not acceptable. That means the conclusion is, if the grid is strong, that is better. If the grid is weak, that means short circuit current is less. That means the critical clearing time is conservative. So we need to check that whether the grid is weak or strong, right? So this is factor number two. There is another factor which can have impact. Factor number three, that is the generator inertia. Generator inertia. So instead of 2.5, let's say this is 4. This is also 4, right? And we will return back this short circuit. Previously it was 40, so we'll change this as 40, just to compare, apple to apple. Okay, so what we have done, we have changed the inertia. Previously it was 2.5, now it is 4 for this prime mover and the generator. This is the only change what I have done. And with respect to that, let's check what are the changes here in the critical clearing time. So here you can see 110.4. That means it is reduced. That means it is reduced compared to the previous one. So what is the conclusion? The conclusion is, if the inertia, generator inertia parameters are higher, then system is more stable. That means critical clearing time can be flexible. Means you can go, maybe instead of 350 millisecond, maybe you can go 400 millisecond or 450 millisecond also, you can get the buffer there. So this is factor number 3. So as a conclusion, what are the factors? Factor number 1, this is the location of the fault. Factor number 2, grid parameters, grid short circuit level, whether it is strong grid or weak grid. Factor number 3, that is the generator inertia. So mainly these three parameters will govern the critical clearing time to save the generator or to maintain the grid stability, right? So I think this entire video is helpful